director of the Waterloo Autonomous Vehicles Laboratory. His research interests lie in the areas of autonomous aerial and ground vehicles, simultaneous localization and mapping, nonlinear estimation and control, and multi-vehicle systems. Today, his speech title is MultiCamera Localization and Mapping for Autonomous Driving. Please help me welcome Dr. Waslander.
This is wonderful. Thanks for all coming. I can now say that I've talked to a packed house at Berkeley. This is wonderful, wonderful stuff. So I'm from the University of Waterloo. It's a great little university in Canada, in Ontario, about an hour west of Toronto. We have an exciting lab, and sometimes it is summer in Waterloo. I've been working extensively on aerial vehicles and drones in particular, quadrotor UAVs, for the last decade. And so some of the platforms we've been working on, and I'll talk a little bit about both aerial vehicles and autonomous driving today, so I want to introduce a little bit of everything. I've also worked extensively on ground vehicles, and particularly rovers for planetary exploration. And over the last couple of years, I've been moving into autonomous driving. First starting with a little racing robot in 2010, and then moving on to, these are 1/5 scale BMWs. I don't have a fleet of 4 BMWs. And then finally moving on to a full-scale vehicle just this last year. So we call our self-driving car at the University of Waterloo the Autonomous. And we have a wonderful facility, and then we have our own 1.2-kilometer test track, which we can book regularly and do all our experiments there as we prepare for public road driving and roll out a bunch of features on a new vehicle. So this project really kicked off in earnest in about June of 2016. So what you're going to see today are relatively new results on the autonomous vehicle and a bunch of historical or more finished results on aerial vehicles, so I'll do a bit of both. So to quickly summarize what happened on the autonomous driving side, we were invited by Renesas, Electronics America, and QNX. So Renesas builds automotive-grade safety chips for autonomous vehicles, and QNX is a real-time operating system company. And we were asked and invited to build a demonstrator, so basically an autonomous driving demonstrator that had a whole swath of features, and could we do it in 6 months, and how could we proceed? And so the goal was GPS path tracking, so we kept it relatively simple on the localization side, vehicle and obstacle detection, motion planning, V2V and V2I communication, and triple model redundancy. So we needed to be able to build this code in such a way that it could run simultaneously on 3 separate processors, and the results could be compared between the processors, so hard real-time requirements there. We needed to be able to do a fail operational emergency pullover maneuver, which would ensure that the vehicle could recover from a hardware failure. And all of this had to be done on 4 ARM57 cores, so a tiny little computational payload, and 1 gigabyte of memory. So we really restricted what was available for us, and it drove all of the decisions we made on the algorithm side. So we had a team of 20. We were racing after this deadline. They came with a beautiful car, and we got wonderful T-shirts made. So it was a really fun experience. And really, we broke the problem down into 4 main areas. So GPS tracking, trajectory tracking controller. This was fairly standard. A local motion planner that had to be extremely lightweight. And so we focused in on state lattice estimation, so generating multiple trajectories and selecting only those that were collision-free or didn't conflict with any obstacles. We then did LiDAR-based obstacle and vehicle detection, so building an occupancy grid map on the fly and detecting a specific vehicle in that space. And then we ran all of this on these 3 autonomy cores with an ASIL-D monitor that made sure that when there was a failure, one of the processors was stopped, essentially the system would default to a fail-safe maneuver. So we took all this to CES after about 3 months of testing on the actual vehicle, and navigated at low speeds in a test lot. So you see 3 different videos here. The top is the parking lot at CES, and for 4 days straight this code ran without a single failure. And nobody was hurt in the making of this video, and we had a wonderful experience doing it. Here we're running the same preliminary tests up in Canada, and so you can see the difference in the environment. We had a lot of snow that fall. And then finally over here you're seeing the simulation environment where we're navigating that obstacle course. So there's some interaction with the vehicles, et cetera, et cetera. So this was a wonderful project. It allowed us to build a baseline vehicle, get us to the point where we have our own self-driving car with code that we can modify and adapt, and set the stage for what I wanted to talk to you today about and where we're heading in the future. So building these self-driving vehicles in such a way that they'll be able to navigate through extreme weather conditions and precipitation, snow cover, and deal with a larger range of environments than what they're currently capable of. Awesome. So today I'm going to talk a little bit about graph-based simultaneous localization and mapping. And I know that this is a fairly broad audience, so I wanted to get a quick sense of how many people already work on localization and mapping or know the fundamental concepts. We've got about 5 or 6. Okay, great. So I included a few slides up front just to sort of ease you into the process and what we're talking about. And so those will be nice to walk through. Then I'll talk about our main work on multi-camera parallel tracking and mapping, so an extension of the famous PTAM algorithm from 2008. Then we'll talk a little bit about degeneracy analysis. So this is really the crux of the problem when dealing only with multiple cameras, is identifying under which conditions you can properly identify your own motion in the environment from the camera data. And then finally, I'll show extensions to this base work, where we bring it into the winter condition driving situation for ground vehicles. Lovely. Okay, so what we're going to talk about today is a feature-based simultaneous localization and mapping. And so by that I mean that as we navigate through the environment, we're trying to identify the motion of the vehicle through the environment. So we're trying to come up with an estimate of the robot's translations and rotations through the environment. We're also trying to identify a set of features in the environment, so think of corners or edges, whatever it happens to be. And each one of those features is defined by its location in the map. And so here we have an XYZ coordinate for a point feature. And then we stack all of these features into a map M, and we stack both of the sequence of all individual poses in which measurements were taken and the map into a large vector X, which we call the state of our feature SLAM system. And similarly, we can constrict our view to only the current pose of the robot, as well as the map we're trying to define. And so that's a shorter state. So the state at time t would involve just the map and the robot's pose. So given that we have this structure for the system, we then set up motion models and measurement models. So both of these essentially give us information about the evolution of the system and then measurements that are recovered from the environment. And so the first set here defines our translations or our motions from the robot pose and the inputs provided at time t-1 to the pose at time t. And so whatever nonlinear process you'd like to include there, right? A bicycle model, a high fidelity aircraft model, a quadrotor model, all of those can be used in this motion model process. And similarly, we have measurements here that are going to give us information not only on the robot state itself, but also on the map features that we're detecting in the environment. And so the interesting part about localization and mapping is that you're doing all of those things at the same time, right? So you're trying to detect, oh, sure.
Features are static.
Features are considered static, yes, absolutely.
Not other vehicles.
No, they're static features in the map, so there's no dynamics associated with features. Yes, absolutely. And in fact, a big piece of what we do is eliminating all those features on moving objects in the scene and simply ignoring them. Yeah. Excellent. So the state prior then defines where our map origin is, right? And so this basically sets us up with an initial position, and we simply call that the origin. And we know that origin with absolute certainty, so there's no uncertainty associated with that state. And for both the motion model and the measurement model, we can define additive Gaussian noise and therefore a distribution over possible states arrived at given a set of inputs, and similarly distribution over measurements given the state that the system is currently at based on a Gaussian noise model. Right? Okay, so this is the structure of our problem, and what we'd like to do really is navigate through the environment starting from some initial pose that we've defined, identify some features in the environment that are visible, and so each of those features is then measured and tracked from the current location of the robot, and then move through the environment by applying an input to the robot and repeating the process. Okay? And so what we end up with is we end up with a set of constraints on the various unknown elements of the estimation problem. So we end up with a constraint between the pose at time 0 and the features that were observed at that time, and similarly a constraint on the relationship between the pose at time 1 and the pose at time 0. And so we keep doing this as we move through the environment. Every now and then we identify features that we've observed in the past, and those features then have multiple measurements and again further constraints that allow us to improve the overall performance of our mapping through the environment. And this process proceeds as we go through the world. Okay, so that's the idea behind the graph SLAM or feature-based SLAM optimization problem. So to actually solve this problem, what we do is we form essentially a maximization over the set of all states, so both the map and the entire history from time 0 up to time t. And we're given all of the measurement information that we collect over that history as well as all of the inputs that we apply to the vehicle. And so we can apply Bayes' rule, we can apply the assumption of the Gaussian distributions, and we can convert to a negative log likelihood form of that cost. So I'm bundling a whole bunch of steps into this one little sentence here. And what we end up with is we end up with a minimization that we know how to solve. And that's essentially a quadratic minimization with nonlinear error terms relating the state at time t to the expected state generated by the motion model, and similarly the measurement at time t to the expected measurement model given the state that we provided, right? So we can decide on how we weight these individual factors. We can decide on which measurements associate with which features in the environment. All of those are interesting aspects to the optimization problem. But really what you're doing here is you're solving this large nonlinear optimization, right? And so there's been a lot of fascinating work in this area over the last, I don't know, decade, maybe longer, 2 decades, in trying to extract the structure of this optimization problem and solve it rapidly. And so there's some really great packages. Google has Ceres, G2O has been around for a while from ETH, and another great example would be GTSAM from Georgia Tech. Okay, and so what does that do to our graph picture? Well, it means that every one of these individual constraints between a pose and a feature or between 2 poses can be defined as this factor or this component of the cost function that needs to be minimized. And so essentially what you can think of all of the individual locations of the features and the poses of the robot being balanced against each other based on the information collected in that pose graph. And so that's the problem we're trying to solve. That's the graph optimization to determine the motion of the robot through the environment and a map of feature locations that were observed along the way. Okay, so that's what we're going to try to do today. We're going to take one more step in terms of how we're going to solve that problem, and I'm going to move to a tracking and mapping combination. And so what that's going to mean is essentially that we're going to build on work from Klein and Murray in 2007 called parallel tracking and mapping. And so we're going to divide this task up into 2 aspects, right? So the first thing we're going to do is the same as before. We're going to define a location, and we'll define a set of features in the map. And then as we've identified the locations of those features and constructed a map that we can work against, we don't have to update our map at every time step. Instead, what we can do is we can track our motion against the existing features in the map. And so what we do is essentially for every one of these poses, we look for mapped features, and given those mapped features, we can simply perform a localization or a motion estimation based on those measurements and assume that the map features are statically known with some uncertainty associated with them. Right? Then, when we've moved far enough through the environment that our map is starting to become unuseful, we can add an additional location, or a keyframe as we call it, that basically defines a new position in the map and perform yet another map optimization or graph optimization to expand the visibility of our environment.
Accounting for scaling.
Are we accounting for scaling? Yeah, so right now I'm talking generally. So if we're thinking of monocular camera, absolutely you need to account for scaling with some other sensor. But if you're talking about multiple cameras, we can actually recover scale directly from the camera measurements.
But as you move, the scale changes.
The scale of the world should stay fixed. And the motion, and so as you move through the environment, if you're not connecting the dots, so if you're not actually continuously overlapping your map, then you run into trouble with scale, absolutely. But given that you can resolve scale at some point in the process, you can maintain that scale. We'll talk about this a little more as I get further into the multi-cameras. Okay, so from there we can see the same process. So we go around we go around the graph in this manner, and what's really valuable about this is that we can do these localization steps significantly faster than we can do the complete optimization over both the graph, over the entire graph, right? So the optimization problem that includes both the entire history of the robot's poses and the entire set of features in the environment is a large optimization problem. but the optimization over simply the location of the robot at the current target, at the current location, given the features that were observed, is much smaller and is faster, and can be done in any number of ways. And so what it becomes either a single time step EKF, UKF type update, right, where you have a slightly reduced cost function, or you can do a sliding window filter, which has proven to be very robust and reliable, and yet still relatively computationally convenient. And so what we can do essentially is that same optimization, but over a sliding window, over some fixed number of images in the past, and only look at basically the effects of the motion model and the measurement models on that optimization. Wonderful. Okay, so I've now basically formulated a general problem. I've given a method that we can use to track our motion through the environment and similarly develop and construct this map on the fly. And so we went ahead and tried out the PTAM. It was publicly available. They give a great code base and a wonderful data set to give it a try against. First thing we noticed was, of course, it doesn't work. Right? This is the standard of every open source package you ever try. You put it in some slightly different environment, and it's a big challenge. And so our big quest was really to define how we could improve this to be more robust and more reliable in a wider range of environments. And the real weakness or the brittleness of this optimization is then in the ability to track features for a long period of time. You can imagine that the ability to triangulate the location of the feature in the environment depends entirely on the range of viewpoints from which you can see the number of measurements and the breadth of those measurements from which you're observing the resolution. Sorry?
And the resolution.
And the resolution, absolutely, absolutely. And so we were looking for a way to do this parallel tracking and mapping onboard aerial vehicles. And so we very quickly moved to the idea of wide field of view cameras that could track features for a really long time within the camera, and then multiple cameras allowing us to track features from different viewpoints and avoid evasions caused by objects moving through the environment. So we weren't able to use lasers because they were too heavy and expensive, and monocular cameras, as we were describing before, have this challenge in that they can't completely resolve scale. So a couple solutions to that are to include inertial measurements or include multiple cameras, and that's what we did. The drawback of the multi-camera approach is that it's an extremely large amount of information, and especially if you're trying to process it in real time onboard a UAV, this is a very restricted hardware setup in order to achieve that goal. And so we have very large data acquisition rates, and the standard problems with all monocular SLAM solutions, which include illumination, motion blur, and feature correspondence issues. Okay, so we switched to wide field of view cameras. We put multiple cameras on our quad rotors pointed in different directions. And the initial requirement is, of course, that we need a camera model that satisfies the lens assumptions that we have. So the standard pinhole camera model doesn't apply. And so instead what we do is we use this model developed for diatropic and catadiatropic lenses, which includes the ability to project all of the points in the environment onto a unit sphere instead of onto an image plane. So once you've projected them onto the unit sphere, you can then perform a mapping from that unit sphere onto an image plane through a projection function that's defined as part of this model. And so this is the Taylor camera model. It's essentially a Taylor quartic polynomial in our case, but it can be of any order you'd like. And basically what it defines is it defines that mapping from the unit sphere onto the image plane. And so we have sort of the picture here. Here's our unit sphere. Here's a point out into 3D space that gets projected onto the sphere. And then the question is, how do you take a point from this and match it onto the camera imaging sensor? So this is just calibrated through standard target calibration. And once you've defined the parameters of this model, you can then map from the 3D world onto the image plane. And similarly, you can invert the model and map from the image plane out to the 3D point in the environment, and therefore define an inverse projection function that takes you from the point on the image plane to a pixel measurement, essentially, or from a point in the environment to a pixel measurement. So there we go. Okay, so now we can take any wide field of view camera and convert a measurement from the 3D environment into a pixel location. And so now what we do is we start to construct the multi-camera problem. So here we have camera 1 and camera 2 attached together by a rigid rig. So there's a static and calibrated known baseline between these two camera centers, right? And so you not only know the distance between the two camera centers, but you also know the relative orientations of their coordinate systems. And these cameras are moved through the environment and are detecting features as we described previously. So camera camera 2 sees the green features, camera 1 sees the red features. And so we get a measurement of a particular point in the environment, and we've observed that point in camera 1 at time step 1, or keyframe 1 as I've called it. And then the camera system moves to some new location and takes additional images and rediscovers that same feature in the environment. And what I have is I have a transformation between the two keyframe locations defined by a rotation and a translation. And similarly, I have two measurements of the same feature in the environment in the two camera locations.
Steve, you know this feature?
This is the corresponding problem, essentially. So I'll get to that in a second, but the real issue here is that sometimes you do, sometimes you don't. So we use a particular feature detector, we use a particular feature descriptor, and then we do a matching process. And that works 80% of the time, essentially.
Assume that things don't change.
Things don't change. No, this is still a hard problem. Yeah. And so, in fact, you spend a lot of an old problem. Very true. Very good. You spend a lot of time trying to eliminate incorrect correspondences before they corrupt either the mapping process or the tracking process. Okay. So going to a more general picture then, as we're moving through environments, you have the same at 3 different keyframes. And we're interested in is trying to describe how define the state in camera 2. So the first time we observed the feature was in camera 2, so define a position for that feature relative to the camera 2 frame, where it was when it was located at the keyframe 2 position, right? So the position of this, or sorry, the transformation to this camera 1 center at time step 2, or where keyframe 2 is included, is defined as one of the optimization variables. And so we can then associate this feature with that particular keyframe and define its position based on that initial measurement as to where it is in that location.
Sorry, you know the entire position of the point, or you know the projected?
Exactly. You only have the projected measurement, right?
Okay.
And so what we do is we define it in terms of a spherical coordinate system.
Okay.
So we have a fairly accurate bearing to that feature and a completely uncertain depth.
Distance.
Exactly right. Yep. And so, but what that means is you can immediately initialize every feature in your map based on the bearing on the feature, right?
Okay.
And with some default depth or some smart depth if you want to, based on relative features in the environment you're buying. Okay, so given that you have a reasonable initial estimate for that feature location with a very uncertain depth, you can then continue through the environment and then identify yet another position at which you observe that feature. And so here we are at keyframe number 3, observing that feature again. And so now what we need to understand is how we relate the measurement that's received at keyframe 3 from camera 2 back to the definition of that feature just occurred in keyframe 2. And so this works as follows. I put the final solution up here. So the actual position of the feature in the map coordinate frame as captured from the camera 2 transformation, so the transformation to the location of camera 2. Then we transform it through, so this is the map from camera 2 back to camera 1. Then we take the transformation from keyframe 2 back to keyframe 1, which defines the base coordinate frame for our entire map. We then do an inverse transformation through keyframe 3, so this is back out to the location of keyframe 3. And finally, we do the transformation out to camera 2 again, so an inverse of the camera 2 transformation. We then work through the camera intrinsic parameters, so that's our K of 2 here. And finally, we do the projection of the point onto the image.
You have these cameras on the vehicle.
Exactly right, yeah.
What do you do, or how do you account for shaking, which then has an effect on that baseline?
So we mount our cameras rigidly.
Yes, but they are still shaking. Typically what people do is they put a gimbal.
Right.
Do you use that?
Well, as it turns out, I have a few slides later on where I'll talk about how we've extended the method to gimbal cameras. So this is great. Everyone's guessing where I'm going. It's kind of fun. But yes, absolutely. So for the most part with this work, we did it entirely with a rigid structure. And on a UAV with baselines of under a meter, the rigidity is required anyways because of the aerodynamics of the vehicle. It's not great to have moving rotors. And so we can securely mount the cameras at the extremes of the rotor planes and rely sufficiently on reasonably fixed baselines. The vibration actually has a bigger impact
But
than it does on.
vibration can affect your lenses.
Sure, yeah, absolutely.
Look, I have been there.
You know, yeah, no, absolutely, yes, we can talk more about that.
Yeah.
Sure.
Just backing up a little bit, with respect to the density of potential measurement landmarks.
Yeah, okay, so in terms of the features that you observe in the environment.
There's one sensitivity parameter that's buried inside the computation.
Absolutely, yeah, yeah. So what you're looking at there is we process every image for a set of features, right? And that feature description or detection algorithm has a set of thresholds in terms of how many features it generates, right? And so we set that at roughly 500 per image, which works wonderfully if you have very scattered and interesting environments, and works terribly if you have a large blue sky and a little bit of grass underneath you, right? So I think what you're driving at is when you have inconsistency in the texture of the environment, and therefore the features that you'll detect, how does the algorithm perform? And that was one of the big drivers for moving to the multi-camera system, right? In that if you're looking in multiple directions, there's a much higher probability that you'll look at something interesting. And given that you're looking basically universally, it expands dramatically what you can track your motion through. Give me a white wall room, I'm in trouble just like everybody else. Yeah, absolutely. Okay, wonderful. All right, so what we've done now is we've constructed the good old, extended Kalman filter measurement equation, right? And we can now exploit this, and it's that same measurement equation that was defined in our grassland optimization. So we can now exploit this camera model and measurement model for our optimization purposes. So beyond the initial description, in this process is define everything on the SE3 manifold. And so we use box plus manifolds in order to describe operations or addition operations or difference operations on the manifold. And that means that we simply respect the fact that we're operating in SE3 and therefore have rotations that can't simply be added together, right? And so this is a really nice piece that actually adds significantly to the quality of the results, to the accuracy. So guaranteeing that you're working in this space has now become fairly we have between one camera and the next, so that the patch becomes the patch that you would expect to see from that previous viewpoint. Given that we have those two patches, so now that they're basically aligned from the same viewpoint, we then do a pixel-based error. And this seems to be extremely robust to incorrect detections, although it does cause a lot of failures in detections. So we have a reduced number of features make it through this pipeline as a result, all right? But it means that the ones that do make it through are quite likely to be correct correspondences. So given that we start from 500 features from every image, we'll end up with 15 or 20 or 30 feasible features that exist through the process. Okay, so now we've got reasonable matching of all of the features, and then we pass all of those measurements into a nonlinearly squares optimization, and that, as I was mentioning, operates on the SE3 manifold. So even though we're operating 4 cameras on board a UAV, we're able to reach frame rates at 10 to 100 hertz, depending on how much processing power is available. Then, as we move through the environment and we identify new keyframes that we'd like to add to the map that we're constructing, we pass those over to the mapping thread, and this runs independently. It can run completely in parallel from the tracking process, and in fact, we can actually run this on the ground on much larger computing while tracking in the air on our quadrotor. It allows us to basically segment the process completely. That's another advantage of the parallel tracking and mapping approach. And so we're doing that factor graph optimization, purely Levenberg-Marquardt to get a solution. Again, everything's formulated on the manifolds, and we use the spherical parameterizations with analytic Jacobians we've computed from that measurement equation to do the optimization. Okay, so given that we've got new map updates, we pass those back to the tracking thread, and then tracking proceeds until the next update is required. Yes?
So for the feature matching, are you matching between cameras or between frames?
Okay, great question. So what we're doing is we're matching between cameras, in-camera matching. So we're matching for features that we would expect to observe in the map, right? So in the tracking thread, what we're doing is we're identifying that region of the map that should be visible based on our prediction of the transformation to the current pose, right? So we basically segment the map and identify a subset of features that should be visible, and then we match against those directly from the map, right?
Right. So then you said you didn't initialize any depth for them, where your depth is very, how would you project those for those who don't know
Yeah, so there what you're doing is because you have knowledge of your, the initial projections of that, essentially, right? So it takes a little while, once you've correctly identified features in two locations. If you have a lot of uncertainty on depth, you end up with a challenge there, absolutely. But essentially, for small baselines and small variations, even that depth uncertainty isn't that important. And then once you've moved only that small amount, you can actually already start to train. Right? So
Okay, so
over a
and then
small search radius, you can still identify.
You won't have the feature matching rejected because it's still in the same image, and that
Exactly.
past projection will be roughly.
Exactly, yeah, and you refine it obviously, and so you immediately get a strong depth estimate. We're certainly aided by any kind of depth information to features, right? So the tighter you can make that tolerance on the initial depth estimate, the easier the initialization process is, right? And I'll show you results where it takes us about 30 seconds to essentially converge to a consistent map. And once that happens, we're in good shape. Yeah. Excellent. Okay. So here it is in practice. So we're flying a UAV here in the indoor flight arena to get a sense for the actual accuracy with which we can do the optimization. And what we've done here is we've done the flight, and now we're tracking against a map that's been constructed at the end of the flight. So this is the ideal case where we've beautifully constructed a map, spent a half hour doing an optimization, and the map is now available for that environment, and we're simply analyzing our tracking performance relative to the features defined in that map. And what you can see here essentially is that we're maintaining position accuracies on the order of 1 centimeter. And so this gets close to our Vicon tracking capabilities, right there on the order of 1 millimeter. And so, but this is a really exciting result in that, that's really precise positioning capabilities for a pure camera solution, right? And similarly in orientation, we're within about ½ a degree of the detected orientation of the vehicle. So this is really an exciting result. And here we're operating, we have a couple of advantages here, and I'll point them out, academic honesty and all that. So what we're doing is we're inside, you'll notice, right? So the lighting is very consistent. We're in a busy environment, so there's wonderful features on every surface, right? You might have noticed that immediately. And similarly, we're not moving dramatically. So the motion of the quadrotor itself is not affecting our ability to capture accurate images. So all of the images are crystal clear, right? So this is an ideal case in terms of the tracking performance that we can achieve. But nonetheless, it's a really exciting result because it really is a high level of accuracy for quadrotor flight. So here's the final path on top of the Vicon ground truth. And what's also really exciting about this is that there's really no dependence on overlap for the solution that we've produced, right? So we have a really wide field of view cameras, and in fact, those cameras are overlapping in some locations in the video, so you can actually see some common features of the environment. There's the people here, and the people are standing here, for example, as well. And so what we've done is we've actually masked out any overlapping regions in this result. So with non-overlapping cameras, we're able to produce basically the same level of accuracy as when we simultaneously observe features from 2 cameras. So there's no need for overlap in the systems that we construct, and that means that we can maximize the extent of visibility or minimize the number of cameras we need to get full surround of the environment. Now here's the real crux of the issue, though, is that when we talk about non-overlapping systems, we have an issue in terms of scale resolution. And so this is at the beginning of our talk. And that scale resolution needs to be defined in the map. And so the way we're resolving scale when we don't have overlap between the cameras is we have a calibration, a known baseline between camera centers. And so even though we can't observe features at the same locations, we can resolve that scale based on the knowledge of the distance between the 2 camera centers. There's only one explanation for how the camera moves and sees the features in the environment. And so there's only one scale that can be observed. There's a sensitivity to scale in that process. And so what it means is that we have to first construct that map. And so here we are flying through the environment, and we get about 30 seconds out before the position errors drop back to those levels you saw, about 1 centimeter and about ½ a degree. And before that, the errors in the map themselves are contributing to our tracking errors, and therefore we don't get the same level of accuracy as we saw in the other video. So here we see the effect over the entire trajectory. We see a gap in the accuracy until the point at which the map is consistent and actually captures scale properly, and that manifests itself throughout that trajectory. We put it on a quadrotor and flown it outside, And so here's the same process outside, and we're comparing here overlap with non-overlap in order to give you a sense for how we're doing in terms of accuracy. And so the issues with going outdoors are, of course, that the motion of the quadrotor are much more significant, so pitch and roll cause large variations relative to the walls that are visible. The features are much farther away, and so the triangulation of those features from the quadrotor is harder to achieve. And so therefore, overall, you see a degradation in performance, and initially we end up with errors in our non-overlapping field of view on the order of a meter. Right? So again, we're doing better than GPS outside, so it is quite helpful. And again, we can make the claim that we don't need overlapping cameras to track features and track our own motion in the environment. So you can make your choice about how you'd like to position your cameras as you're flying through the environment.
Might be jumping outside the scope right now, but how about IMU integration?
Absolutely. So none of this work includes IMU integration. It's an actual solution to that same scale resolution problem. It's been well demonstrated. So yeah, absolutely that can be integrated, and that's an area of future. Okay, so we closed the loop on this quadrotor with that image-based localization solution or localization mapping solution. And what you can see essentially is reasonable performance of the quadrotor flight control using that vision-only solution, with the exception of this first segment, right? So, and what's interesting here is, of course, there's a really dramatic viewpoint change on takeoff, right? You start on the ground, all your features are nearby, plus at the horizon, and then you jump up in the air and suddenly all of the features you observed are way down below. And so there's a dramatic error here that's challenging to resolve in flight, and it simply takes time, once again, for that map to converge before we can do the control of the vehicle. But other than that, once the map is established, once scale is known, the tracking performance is reasonable based on the wind effects and whatnot that cause the vehicle to navigate through it. Okay. So we move into degeneracy analysis next. So the idea here is that we've got this wonderful solution, but it turns out, given 2 cameras or even given 3 cameras, there are in fact particular motions that exist that cause the optimization problem or the motion estimation problem to become degenerate. And so I wanted to quickly walk through a bit of the analysis that we did here to demonstrate how those degeneracies occur. And really, it's sort of a nice story. So what we have here, once again, is our cameras and their positions. So this is the camera rig at keyframe 1, or the first position, and this is the camera rig, once again, at keyframe 2. We observe 2 features in the environment, and in fact, we'll do the same thing. We'll observe 3 separate features simultaneously in each camera. And so we define essentially the translation between the 2 camera centers as the vector f. We define the baseline between the 2 camera centers as the vector h. And we define the motion independent of that translation as g. And then similarly, we define the depths to each of the features, feature I in camera 1 and feature j in camera 2, as r and s respectively. Okay, so given that we have this, the state that we're trying to estimate then becomes the depths to the features. So here's a 3-feature set, and similarly the depths to the features in camera 2. The transformation between the 2 keyframes, and then the bearings, so theta and psi, to each of those 6 features that are observed in each of the 2 cameras. And when you look at the Jacobian of that measurement equation for all of the states that we're interested in, and organize it based on the cameras and the keyframes that we're trying to estimate, what you see is you get a really interesting structure, a really clean structure for that Jacobian. And so the degeneracy analysis of this 24 by 24 state measurement set actually becomes reducible to the block elements of that matrix. And so we can focus in on the more compact representations. So here we have that upper left block of the Jacobian matrix. We can do some row operations to reduce it to the following form, and then we can quickly identify the conditions under which that upper block is ranked efficient. And similarly, we can now focus in on this bottom block, which is now completely dense, and all other components are actually manageable by a separate process. And it turns out that there's a really neat characteristic for this block that becomes visible. So it turns out that each one of these rows can actually be interpreted as a Fluker line. And so these are coordinates for lines, 6 coordinates that satisfy the following expression. So given that this is the definition of the coordinates, so qj and qj prime, we have to have that these two aspects are perpendicular, right? So that the dot product is 0. So we satisfy that condition, and what that means is we can now describe these lines in such a way that we can form the determinant of this 6x6 matrix, and that reduces to a quintic polynomial that we can numerically evaluate. And this is kind of a really neat idea. So we can now define the surface of motions for which the measurement equations are degenerate. Right? And so this means that we can detect those motions that the camera cluster will execute that will lead to issues with the tracking performance and with the mapping optimization problem. And what does that lead to? Well, it led to a total of 9 different conditions, and 2 of which were already visible in the literature, which was really reassuring. And the first one is that any concentric circle of a 2-camera rig without overlap between the cameras is degenerate. And even a concentric circle with infinite radius, which would be traveling forward in a straight line, right? Which was death to all of our quadrotor dreams, because we tend to travel in straight lines fairly frequently. As soon as you migrate to 3-camera clusters, however, the set of possible degeneracies decreases dramatically, and in fact, the only one we observed was a rotation directly in the plane of the 3-camera centers. And so that's far less restrictive, of course, and by going to 4 cameras, we were unable to identify any degeneracies, and that meant that you're safe in terms of any degenerate motions for those kind of camera clusters.
What this suggests that what you really want is a panoptic camera.
Ah, okay. Yeah. A panoptic camera. You didn't have to look that up. That's great.
Yeah.
Okay.
It's basically an array of.
Ah, wonderful. Yeah. So, but anything beyond 4, and there's no longer issues. Panoptic would be just, I guess, surplus of his visual data.
Yeah.
That's wonderful. Okay. All right. So for sorry?
You said that there is no overlap in these in the cameras, because originally you were saying 3 features were saved in both cameras.
Sorry, 3 features, 3 independent features
in
each of the cameras
okay.
in both keyframes. Yep. Sorry about that. Yep, absolutely. So we're not relying throughout this analysis on overlap.
Okay.
Yep. Yep. So each feature is considered completely independent in each of the cameras. Okay. So for the final piece, I want to quickly show you a little bit of moving back to this snow problem that I started with. Really what we're looking at is taking this work in multi-camera clusters and mounting it on board the autonomous driving vehicle and then attempting to do localization in adverse conditions. So it's a little bit hard to see, but this is some recent data we collected while parked on our test track. And this was literally, I think it was January, so this is fresh off the press. And what you can see here is LiDAR and vision data from one of the cameras mounted on the crossbar above the vehicle. And you'll notice that even the light snow, it's a little bit hard to see in this, so it's a light snow slowly covering the roadway, leads to significant noise in the LiDAR data. So it's amazing that you can actually detect snow with LiDAR, but there it is. And similarly, the visual data has that same snow speckling, right? So what this means really is you have to rely a bit more significantly on the tracking aspect. The instantaneous detection, there's going to be artifacts in the images that are potentially challenging to remove. The other thing that I found really fascinating was that you can actually detect the tire tracks in the snow here, right, in the LiDAR data. So it turns out that there's a lot of really relevant and valuable information even in the LiDAR data in the precipitation environment, or in the snow accumulated environment. So there's a lot of hope for this problem. And we're just starting on it, so I won't show any results in this area, but it looks like we can do a lot of reliable pose estimation, localization, and mapping, even in these snowy environments as a result. So here's...
If you could have an illumination that is sensitive to the granularity of the snow.
Ooh.
Okay.
Yes, a granularity sensitive illumination.
Because then you get different projections from different orientations of, think about it as like pebbles.
Yeah, absolutely. And so on the snow surface itself,
Yep.
you might still, well, you'll see what we've done in that regard.
Yep.
It turns out that, yes, through some manipulation of the images, you can still extract interesting features from that white snow surface. And so we'll see that in just a second. So here's a couple of static images of that same data. We have a trinocular camera rigged on top of the vehicle. And so you can see some of the challenges. What this does, relative to the lab environment that I first demonstrated our MCP-TAM results on, is that there's almost no features in this white environment, right? All of the features end up being at the horizon, which are extremely poor features for tracking your own motion, right? So translation becomes less and less well restricted. Similarly, extreme lighting variations and shadows in nighttime in snow environments and extreme ranges in terms of the sensor data that you collect make the problem extremely challenging. And then of course, just last week, I'm here on sabbatical for the year, so just last week, I took my kids up to Tahoe, and sure enough, I saw this. So these are shots from my phone as I was parked in the middle of the road trying to decide what direction I should drive in. So, you know, I thought we were a little bit unique in Ontario in being able to do snow driving, and then it's a whole other level when you drive yourself up to Tahoe, 20-foot snowbanks, windshield wipers, and glaring sun the next day. Anyways, I'm excited to drive our car back and give it a try. All right. So the final piece I wanted to talk about today was a couple of improvements and extensions we made to the MCP-TAM framework to specifically operate in snowy environments. And we did this work on a ClearPath Husky robot. ClearPath is a Waterloo company. And those of you that have seen these robots or used them, much appreciated. 2 of my graduate students founded the company back in 2009. So this was the environment we were operating in. We were driving in a relatively sparse, snow-covered field. And navigating with some nearby obstacles, but primarily dark obstacles out at the horizon. And so what that does is that really drives you to try to find ways to use the snow-covered environment for navigation. And so the first thing we did was look at ways that we could refine the image in order to extract features, right? So the nominal image is here up top. It turned out of all the things we tried, it was really just histogram equalization that allows you to enhance shadows and dramatically improve feature reliability. And so even tried contrast limited adaptive histogram equalization, and that turned out to be less effective. The other major benefit, major component of our approach was to identify the horizon reliably and then focus features for localization below the horizon line. So those features at the horizon or above are relatively useless for translational and rotational for translational localization specifically, but the horizon features are really good for restricting your rotation, right? So your heading is well defined by features at the horizon. So we used the 2 sets of features separately and corresponded above and below the horizon as a result. And so that led to the following improvements to the map. So our global histogram equalization led to a map that drove through the environment and returned quite nicely to the central point. And the adaptive localization at 2 different scales led to significantly worse results. And it wasn't even worth plotting the baseline MCP-TAM results. That was absolutely hopeless. It's just a mess of points. It has no idea where it is, essentially. So we're completely lost without any kind of pre-processing of the images. The other thing that really became apparent was that as you're moving through this environment, particularly with this steer vehicle, there was nice straightforward motion followed by extremely jerky rotations, right? And so that led to very bad images, highly blurred, corrupt images that were really poor sources for keyframes. And so what we did was we looked at methods that we could evaluate keyframes prior to their insertion in the map, and therefore try to identify those sets of images that are going to give us the most useful information for constructing our map as we move through the environment. And so this last idea, we called it there's 2 approaches essentially. One is forward-looking and one is reverse-looking. So the reverse-looking approach tries to maintain the accuracy of the map by refining estimates of the feature locations that already exist. And so we did that based on assessment of the entropy reduction that would recur from new features that were included. And then finally, the predicted point feature entropy reduction was a process that essentially tried to predict what features would be visible in the future, and then add new features to areas of the map that did not have significant features at current point. And I won't talk about that last piece. Okay, so the keyframe selection for the map. Essentially what we're doing here, once again, is we're returning to that measurement equation and defining the Jacobian of that measurement equation for particular points that are already in the map. And then for a set of images that we've collected in a buffer since the last keyframe, we can evaluate how much new information is going to be available about that point feature based on literally a simple EKF update. Right? So this is your standard EKF update rule here, and it basically provides us with an estimate of how much better our knowledge of that point location will be given that we insert a particular keyframe in the image. And what we can do is we can simply sum this over all of the visible features in the environment, and then select that set of images that provides us with the most information about our existing map. And by most information, I simply mean the reduction in the entropy of the uncertainty distribution about those features. And so this worked out really well. What's nice about this is that it also immediately incorporates the Taylor camera model, right? Because you have your full measurement equation. And so it understands that features that are observed at the center of the camera are far more valuable than features that are observed at the extremes because of the projection of all of the information from the environment onto the image plane. And so that's immediately captured in our evaluation of new information going into the map. And it means that we have a really nice connection between, or we have a strong representation of that information that's being recovered. And so once again, I can show the entropy-based keyframe insertion leads to a sparse map because we have fewer keyframes in the map. And it leads to a more consistent representation of the motion through the environment, right? And arriving at that same center point once again. And when we simply insert a keyframe every meter or every 2 meters, we get significantly degraded performance as a result. Okay, and there's finally the maps that result in, here's that final location where the vehicle returned to its original position. And so with that, I think I can conclude beautifully, just a little bit over time, I think. And so I wanted to say our future work is going to be moving more and more into this extreme environments for autonomous vehicles. So we'll be taking those same algorithms that we've just described today and move them on board the vehicle. And this was just a lovely shot here to end the day. Drones watching autonomous vehicles driving down the road. Doesn't get any better than that. Thank you very much for your time.